session, we will introduce the Pareto analysis. This was originally used by Vilfredo Pareto, who was a 19th century Italian professor of political economy. And he observed that the top 20% of any country's population accounts for more or less 80% of its total income. And this became then known as Pareto's principle of unequal distribution. And why is this interesting for us? Because Dr. Juran then extended this principle to quality control. So our learning objectives are to understand how a Pareto analysis helps to identify the vital few from the trivial many, and how this can be applied in the DMAIC process improvement cycle. We also want to be able to perform a Pareto analysis by ranking causes and creating a Pareto diagram. Let's just look again at our Six Sigma roadmap and our problem-solving strategy used in Six Sigma. Here we have Y is equal to Fx, where Y is representing the critical to quality parameters that the customer values. And this is then a function of the parameters, the X influencers, the parameters that influence or affect the Ys. And as we move down our DMAIC cycle, what we want to do is to narrow down all possible X influencers to the vital few, the critical few that have the main impact. And this is then done here in Analyze. We have a cause and effects analysis where we're identifying critical X's, and then we're establishing their influence on the Y's using, for example, designed experiments, correlation, regression. And in this section, we want to focus on how we can narrow down to the vital few using a Pareto analysis. The Pareto analysis is used in situations to help prioritize the vital few from trivial many opportunities. The Pareto analysis is used when there are several opportunities to choose from. For example, one project may have to be chosen as the first one from several project opportunities. Or one defect category may have to be addressed first from among many defect categories. A Pareto analysis allows you to focus on the most frequently occurring defect types. It helps you to decide which assignable causes, for example, defect types to eliminate first, or in the other case, which project to start first. And as I just said, the method is based on a distribution proposed by the Italian researcher Vilfredo Pareto to describe how a small proportion of people in the free Western societies controlled a large proportion of the wealth. This is known as Pareto's principle of unequal distribution. He observed that the top 20% of any country's population accounts for more or less 80% of its total income. And this 80-20 rule was then used during the Second World War. In fact, the term was coined by Dr. Juran, who extended this principle to quality control. He stated, for instance, that most defects in production are the result of a small percentage of the causes of all the defects, what he described as the vital few and the trivial many. Now, other examples you may have heard are, for example, 20% of the customers cause 80% of the complaints. Or you have 20% of your product line generates 80% of your company's profit. Same as 20% of your customers are generating 80% of the revenue, or maybe you have 20% of your sales force generating 80% of the sales. This type of separation helps in prioritizing improvement opportunities and in concentrating on the vital few causes rather than spreading effort among the many trivial causes, or concentrating on the most effective project rather than trying to spread yourself out over not so effective projects. The Pareto analysis consists of obtaining data on the frequency at which the different causes have been occurring. in recent history. We want to rank then the causes based on their frequency, with the cause having the highest frequency being ranked first. And then a diagram, the Pareto diagram, is made with the percentage frequency on the y-axis and the causes on the x-axis, arranged in ascending order of rank, or in other words, descending order of frequency. So here our Pareto diagram, you would have here, for example, the causes. And this is a nominal scale. You have cause 1, cause 2, cause 3, etc. And on this scale, we have the percentage frequency, like your histogram. And these are then plotted in ascending order of rank, or this would be rank 1, rank 2, and 3, descending order of frequency. Now we look at an example. So this is again from our textbook. This was the example of the failure of bonds after a curing process investigated by a team of students who was looking at assembling cable harnesses. Now, we had generated for that a fishbone diagram. We had looked then at the process itself. There was a bonding taking place between rubber and plastic surfaces with some kind of bonding material. In between, then there was pressure applied, and there was a curing step where these bonded surfaces were cured in a temperature and humidity controlled chamber. And any bond was considered to be a failure or a defective when it does not meet the strength, when it did not meet the strength requirements. So the students then decided, after doing their brainstorming and coming up with a fishbone diagram, what would be the most likely causes. And they collected then data on 8 different defect categories, which was available over a 12-month period. So as you can see here, in May, there were 14 defective bonds, 14 defectives, 14 problems at the end of the process. 3 were due to the degreasing, 1 was due to bad rolling, 4 to curing temperature, and 6 to curing humidity. So again, this data had to be available. And the input of the experts after the cause and effect brainstorming then helped the student team identify what were the most likely failures. So you can also see, for example, in April and May, the defects here were mostly due to curing temperature and curing humidity. So all of these then defective number of defectives are totaled for each particular defect category. So in total, there were 238 defectives. And to create the Pareto chart, then, the percentage frequency of occurrence for each of these different causes is then calculated. So on this side, we have the count from our 238 to the percentage defect. So here we have 100%, this was our 238 total, our 100% percentage frequency. So, and here you see the different causes of the defectives, and here everything's bundled here together, and others. And then you have the count of 87, well, over 236. The cumulative then is 36.6. And since the curing has the highest count, or the highest percentage frequency, it's ranked 1, and it's plotted first in our Pareto diagram. So these are ranked then, and you can see then in a very clear diagram the count and the percentage frequency, which is then plotted here in the Pareto diagram. So this helps you then this graph and the table helps you then to see the most important causes. So here we've got curing humidity and curing temperature. Clearly, showing a higher impact than everything else. And so these would be the two areas then where you would concentrate. Again, and here these are, if you add these up cumulatively, these two together, this is the cumulative frequency, 60% of all the bond failures are caused by these two. Cause 60% of bond failures in this case study. So going back to our roadmap, this Pareto diagram then, as we said, is helping narrow down many X's to a vital few. And then our next step then would be to see how these actually influence the Y variables and how we can adjust them to achieve the goals of the project.